Hello friends, welcome to short lectures on physics, and today's topic is quantum mechanics, and the book that I will follow is Introduction to Quantum Mechanics by David J. Griffiths, one of the most preferred books. Okay, while discussing quantum mechanics, let me first start with a safety disclaimer that in this lecture I have tried my best to represent each and every point given in the book with some additional information from authentic sources. But if at any point the viewers may have some different opinion or different interpretations, since it's quantum mechanics and it is more misunderstood than rather being understood. So if there are any suggestions or comments or corrections, you are please welcome. And I think there is no harm in giving this safety disclaimer, since Feynman has already said that I can safely say that nobody understands quantum mechanics. So we will start with the chapter 1 of this textbook, Introduction to Quantum Mechanics by D.J. Griffiths. But before that, let us discuss some brief about what exactly is quantum mechanics. The world around you, your laptop, your room, your street, your house, the trees, planets, sun, moon, earth, etc. All the visible things, they all are considered as macroscopic things, and the whole world is called macroscopic world. But we very well know that this macroscopic world is made up of microscopic objects like electrons, protons, or any elementary particles. But even though this is the case, the science for the two worlds is totally different. Certainly, same logic cannot be applied to the seen objects or the unseen objects at the subatomic microscopic level. One can never expect a planet and an electron to behave in the same manner. So the two worlds and their approaches are entirely different. For the first world, we can say about the macroscopic world, whatever you see around you easily, that whole thing consists of this macroscopic world, and basically you, me, or even Newton himself, all things come under the macroscopic world, which is governed by classical mechanics, which follows the Newton's laws of motion. But when we move towards the microscopic scale, that is electrons, protons, neutrons, elementary particles, their dynamics, all these things come under the microscopic world and basically governed by the quantum mechanics. Although quantum mechanics was not introduced from the day one along with the classical mechanics, which means that it had a bit late start comparatively. If I'm not wrong, it is in the late 80s or early 90s. But even though having a late start, today and also tomorrow in future, this subject, this quantum mechanics, will be always there into the physics and is always persistent. Therefore, we can say that about quantum mechanics, na bhuto but bhavishyati. So that's all about quantum mechanics, a very hazy view, or one can say a very soft start to introduce such a big subject. But what to do? I cannot on the day one or the first lecture describe you the literally weird concepts of quantum mechanics, since a doctor does not describe about the pain of the injection in front of his patient before giving it to it. So anyways, let's start the subject and enjoy the subject, beginning with chapter 1, the wave function. The first subtopic is the Schrdinger equation. Now imagine a particle of mass m which is constrained to move along x-axis subject to some specified force, say F. You can see the figure here. The particle is shown by this particular thing and of mass m moving on the x-axis. Now, classical mechanics wants to determine the position of this particle at any given time, say x of t. Because once we know the position, we can go for the velocities, the momentum, the kinetic energy, and whatnot. And all these things can be achieved through the Newton's second law of motion and some mathematics. So basically, we can determine via classical mechanics the position x at a given time t. But the same problem, when taken from quantum mechanical point of view, the approach is entirely different. In this case, we are looking for the wave function represented by the term psi xt. And this wave function can be obtained by the solution of Schrdinger equation, which is shown in the equation 1.1. At present, we can just learn this equation like the energy equation, where the left hand side basically denotes the total energy, and I cut del by del t is the energy operator, which we will be discussing in further lectures. But right now you can just see that the left hand side is the energy, and therefore right hand side has to be the energy, the first term being the kinetic energy part and the second term being the potential energy part. So the solution of this Schrodinger equation will determine the position, and here in quantum mechanics the wave function psi. So if we compare both these mechanics, then these both are analogous to each other. Okay, fine. One thing I forgot to say, that in the equation h cut basically denotes the Planck's constant divided by 2 pi, and I is the root of -1. So coming back, the Schrodinger equation is basically analogous to Newton's second law, of course with few suitable initial conditions, because Schrodinger equation also determines psi for all the future times, just as in classical mechanics Newton's second law did. So this is it, a brief introduction of Schrodinger equation and the particular term wave function. But still, wave function is not that clear which it is supposed to be. So for that, we will move to the second topic, the statistical interpretation. Now, whenever we talk about a particle, we very well know that particle itself means a localized point. Whenever we say that, suppose a particle is placed on a box, let's take an example like this. A particle is placed here, then one can easily find out the perfect position coordinates. Okay, this is the x dimension, this is the y dimension, this is the z dimension, likewise. But now, if I just modify my question and say, imagine a room where a bell is ringing, and I ask you to determine the exact position of the wave. How logical is it? You can in a way say that, okay, the bell is ringing from the center of the room, or from the right corner, or from the left corner. So basically you can define a region, not a particular point, because wave function, as its name suggests, is a spread out in space. It's a function of x for any given time. Then how can such an object be said to describe the state of the particle? This question which arises has been answered by the Born's statistical interpretation, which says about the probability. The probability, which is denoted by mod of psi square, and when mod psi square dx is written, it defines the probability in this particular region or this particular range between x and x plus dx at time t. So with this concept, we will now take an example of a typical wave function as shown in the coming figure. You can see this. The x-axis denotes the probability, and the y-axis denotes the probability, and the x-axis denotes the position. You can see a typical wave function, and there are several points where you can see high peaks, low peaks, almost zero. So you can just make an analysis of this and find out that the particle is likely to find at point A, which is very much clear from the figure, and it is very much unlikely to find it near B or at B. The things are very obvious from this, but this kind of statistics, this kind of probability, in a way introduces indeterminacy in quantum mechanics. Why? Because even if you know everything the theory has to tell you about the particle, you cannot predict with certainty the outcome of a simple experiment to measure its position. Right? In this particular case, you cannot easily measure the position. So, quantum mechanics has to offer only the statistical information about the possible results. See, quantum mechanics plays very safely here. It tells you about the probability, it tells you about some statistical information about all the possible results, which means the particle can be at A, it can be at B, it can be at C or elsewhere. And this indeterminacy has been profoundly disturbing the physicists. So, to make it clear, we can take another small question. Suppose we measure the position of a particle anyhow and find it to be at point C. Okay, the question is very simple. Where is the position? The answer is very simple. The particle is at point C. This is the measurement made by us. Now the question arises, where was the particle before I made the measurement? And there are three answers to these questions. These three answers are like three different dimensions, three different aspects. The first one, the realist position. The realist person says the particle was at C. Now this is very much clear that when I measured, the particle was at C, which means that even before the measurement, it must be at C only. What is the second question in this? So this is an approach of a realistic person, a very practical person, a realist position. But if this is true, then what about the indeterminacy in quantum mechanics? In such a case, quantum mechanics would fail, because to the realist, indeterminacy is not the fact of nature, but it is a reflection of our ignorance. As said by Spagnet, the position of particle was never indeterminate. It was merely unknown to the experimenter. The experimenter did not know that before measurement where was the particle, but the particle itself was not indeterminate. It was fixed about its position. So, according to a realist position, the particle was at C even before the measurement, and after the measurement, as the result says, it is at C again. So this is one aspect, and quite convincing to the practical persons or realistic persons. Now, moving to the second aspect and the most important aspect in quantum physics, the orthodox position. You can just read it out that the particle wasn't really anywhere. It was the act of measurement that forced the particle to take a stand. Now, this is really confusing. How can an act of measurement force the particle to take a stand? But yes, that's the orthodox position. Even Jordan said it. Observations not only disturb what is to be measured, they even produce it. In a way, we compel the particle to assume a definite position. Now, this is quite unconvincing. So, let us take some example of realistic situations. I'm taking two examples here. Please try to relate it with the orthodox position indirectly, not directly, because these examples, as we know, we are taking from the classical world, our own realistic world. But these examples may help to develop how to understand this concept. So just try to learn this. The examples are, okay, whenever we are facing an interview, before going into the interview room, we are very much prepared, very much confident, or somewhat nervous also. But once a person enters the room and sits in front of the interviewers, and if the interviewers are more than furious, or they are more conscious, then the, many a times it happens that the interviewee gets fumbled up. It's just written here in the cartoon, as you see, that I was fully prepared just a minute before I entered. The man thinks this way. Then what happened to me after coming into the room? Now, what happened in this case? Did the presence of the interviewers, did their observation, did their measurement, here measurement is in terms of evaluation. So, did the observations made by the interviewers, or did the measurements made by the interviewers on the interviewee disturbed him, and he fumbled up, and he spoke like anything which he was not supposed to speak? And yes, it happened here. Another example, you can see just that a lady who is already confused seeing a lot many audience in front of her. Now, it is expected that when you come on stage, you have something to deliver, either a speech or a song or anything. But looking at the great audience, sometimes even you and me have experienced that we become overconscious, and at such times we deliver such things which are not actually a part of our speech or a part of our plan. So why this happens? This happens because of the presence of the observer, the presence of the audience, the presence of the interviewers, kind of stage fear, right? So coming back to our physics, please do not relate it directly. This is again I am repeating to develop the understanding. So now coming back to the orthodox position, observations not only disturb what is to be measured, they even produce it, and we compel the particle to assume a definite position. So according to this aspect, the act of our observation gave us the answer C, right? So this is the second aspect. And the third aspect, the agnostic position. Now, who is an agnostic? An agnostic is basically, he is a person who is not interested to answer unnecessary questions. Say for example, does God exist? Along with the three options, the agnostic will choose the last option. God only knows whether God exists or not. So basically, the agnostic approach is to refuse to answer. He is not at all concerned about the previous measurements or the previous positions of the particle. It is like uh, something related to metaphysics, that why to worry about something, right? Why to worry about something that cannot by its nature be tested? Which means when you know that you will be unable to find the particle's position before your measurement, that is in a way reverse timeline, then why to worry about it? So this is that approach. There was an example that Pauli said that one should no more rack one's brain about how many angels are able to sit on the point of a needle. It is very much clear that when you are unable to prove this, then why to waste time in discussing or even trying to get answers for such things? So that is an agnostic approach. But anyways, amongst these three approaches, somewhere decisively we have to believe that the quantum physicists in the past made some experiments, some thought experiments, and confirmed the orthodox interpretation. And according to them, a particle simply does not have a precise position prior to the measurement, which again means that it is the measurement process that insists on one particle or a particular number and thereby creates some specific result. Okay, so for a quantum physicist, the orthodox position has been considered that if you measure the system, you are in a way disturbing it. Fine. So these are the three aspects, but there is one more thing to add. What if I do a second measurement? What if I made a second measurement immediately after the first measurement? Will I get C again, or does the act of measurement, just we discussed it right now, the act of measurement will again disturb the system and we will get a completely new number each time? So this is again a point to think over, and this question is in agreement with everybody. In this case, if a measurement is repeated, then it must give, or it may give, the same value if and only if the measurement is immediately done on the system. Right? Because a repeated measurement on the same particle must return the same value. Indeed, it would be tough to prove that the particle was really found at C in the first instance if this could not be confirmed by immediate repetition. If we again immediately do the second measurement and we get different result, then our first result was also doubtful. Right? So the immediate measurement should give you the same result. Now let us verify this with our orthodox interpretation that was confirmed by the quantum physicists. How does the orthodox interpretation account for this? It says that when we did our first measurement, that measurement altered the wave function. Altered the wave function means, I will just go back to the figure. This was your wave function before measurement. Now, when you measured the system for the very first time, what happened? You got the answer C. Now, this means that the particle is at C. So now this particular wave function will take a shape of a spike. I hope you understand that before the measurement, when we were unknown of the particle's position, the wave function was a spread out. But as soon as we knew the exact position of the particle, the wave function changed to a single spike. And this is called that wave function has collapsed, which you can very well see. You can now not see a wave moving. You can just see, one can even imagine a point here, that yes, the particle is exactly here. Fine. So the orthodox interpretation says that by doing the first measurement, the wave function has been collapsed to a point C. Now, as the nature of the wave function, it will again start spreading according to the Schrödinger's equation. You know that Schrödinger equation has the time part also. So as time will start moving on, the wave function will start spreading out. So to avoid this, to avoid such a spread, we will make the second measurement immediately and quickly after the first measurement to gain the same result. So if ever you want the same result in the second measurement also, then you need to measure the second time measurement immediately. Right? So you will be very much nearby the collapsed wave function and you will get the same result. So this is how the orthodox interpretation justifies this. Fine, I hope so it must be clear. although with confusions. So basically, this can tell us the importance of the word measurement in quantum mechanics. Till now, as studied in the classical physics or in the conventional laboratories, the word measurement did not become so problematic for us. But this is quantum mechanics, friends, and in quantum mechanics, the role of measurement, that's a footnote given in the textbook. The role of measurement in quantum mechanics is so critical and so bizarre that you may well be wondering that what exactly does the measurement means, and some of them have even uh, given their opinions that what is a measurement. Say for example, if you are looking inside a microscope about some dynamics of the amoeba or some subatomic level atoms or molecules, then you are actually looking at the quantum world with a classical eye. Classical eye means the instrument, and the instrument is in a way macroscopic thing. So by using the macroscopic apparatus, the classical apparatus, you are observing quantum mechanical system. So the measurement here means the interaction between this classical apparatus and the quantum mechanical system, as this was suggested by Bohr. Heisenberg even claimed that measurement is a kind of leaving a permanent record. Even Wigner proposed that. Does the measurement involve the intervention of a conscious observer? It is like the intervention in an event by a conscious observer. So there are different opinions from different great scientists about the word measurement, and this happens only and only in quantum mechanics. Fine. So as of now, we conclude here because I can measure the disturbances created in your mind. So let us wait for the next lecture to upload. In the next lecture, we will include discussions on probability and normalization. And if you have any comments, suggestions, questions, discussions, or even corrections, please feel free to write in the comment box, because our motto is to learn. Either it is you who will learn from me or I who will learn from you. Right? Thank you for watching. That's me and my institute. Have a good day.